During your cell growth in a fed batch or continuous batch, or or just a batch, whatever the bioreactor culture you're maintaining, you have to monitor your cell growth. Okay, if you're dealing with maybe prokaryotic cell, you can simply take the cell density using spectrophotometer reading. That's optical density reading. Okay, but if you're dealing with animal cells, you have to take samples and you have to count the cells under the hemocytometer. Okay, there are different ways of counting or determining cell concentration. That's important to make sure that they are under still within the log phase. Also, you need to check the level of nutrients if the cells have enough glucose in there, or if glucose are mostly converted into the byproduct waste, lactic acid, any other byproducts are accumulating or not, because these byproducts are not good for the cells to survive. So you need to, feed the new nutrients, get rid of these. Okay, so monitoring is really important. Okay, and whatever the bioreactor size you use, you have to provide a good condition. So clean nutrients based on UFI quality. Documentation is also important. So all these, common sense requirements you need to understand. And are you using animal cells? Of course, their requirements are more complex. And these days, there are transgenic plants that can make human proteins. If that's the case, then you can just grow up the plants and maybe collect the plant tissue. From those, you can isolate the proteins. There is a possibility. Instead of using a complex bioreactor, you can just grow up the cells. So whatever the cell lines and whatever the transgenic materials you use, your goal is to purify the maximum amount of protein, okay, from whatever cells that you're using. So the technology will allow you to get a lot of return. So if you invest, this much more money, you need to be able to make a lot more proteins. Okay, so a lot of more technology is being invested to make sure that whatever the cell lines will give you the best return in your investment. Okay, because API is the money. Okay, so a bioreactor fermenter, they come in different designs. This is a simple spinner flask. The little spinner is spinning around so that your cells will be continuously being suspended, right? So the bioreactor can be as simple as this design, or it can be as more complex as this bioreactor. So there's a control tower that monitors the threshold, and then you have the bioreactor here, jacketed bioreactor or unjacketed bioreactor. Jacketed is jacketed for the temperature control. It has outer chamber that's filling the inside jacket with water. So the water will cool down the temperature if it's needed. Unjacketed doesn't need the cooling, so it just needs a heat blanket to heat up just in case. And then all those spinner, its controller, it will make the cells spin suspended, and air will be pumped in. So air filter is in there, and other probes will be embedded there, like a DO probe, oxygen, dissolved oxygen probe, or pH probe, and thermometer, all those things. And they are hooked up with this control tower, so it'll do the real-time reading all the time. So if, like for example, pH is dropping down too fast, it's going to give you an alarm so you can do something about it. If the dissolved oxygen level is going down, it's going to also give you an alarm, or it's going to kick in automatically to pump more oxygen in. So it can control those. Okay, so that's what the bioreactor designs would allow you to do. So assembly of the bioreactor is important because you have to do it aseptically. After bioreactor is assembled aseptically, then you're going to introduce your cell line, right? So it depends on the size of the bioreactor. You can, sterilize it within an autoclave, or if it's too big, you're going to have to do it using CIP, clean in place. Okay, and then by shooting the pressurized water, whoopee water, and cleaning solution, and rinse it, and then at the end you have to sterilize it by doing a sterilization in place, steam in place. So you'll generate a pressurized steam in there and close it, and that's how you can sterilize it. Okay, so you have to make sure that you do it well. So your goal is to keep the cells at the late log phase I told you. So late log phase means almost like 1 million cells per about 1 mil. That's the concentration that's required. You have to keep the cells around that concentration. If it's more than that, they are going into the stationary phase that you don't want that. Okay, you have to pass to the next level of bioreactor. So scale up is passing from a small bioreactor. If the cells are running out of space and they reach the 1 million cells per mil, then they have to move to a larger bioreactor, so their concentration will drop, so they'll have more space to reproduce. So that's a scale up or passing. You will do that continuously. Whichever the bioreactor you're keeping the cell at, they have to be continuously suspended using an impeller. So stirring will take place. Okay. So bioreactor can feed different things. This is a perfusion bioreactor design. This is a brand new design of bioreactor that's more popular these days. So we talked about batch bioreactor, continuous bioreactor, and feed batch bioreactor, 3 kinds. And on top of that, there's something called perfusion reactor. Perfusion reactor is, through its design, you can pump in more nutrients, and then you can also pump out the waste from the bioreactor. So since you can feed more nutrients and you can get rid of waste, so you can extend your culture condition long time, so you can get more cells growing within this bioreactor. So within given a same bioreactor size, of course you can grow a lot more cells. That means you can make them happy more longer, so they can give you more API. So you can get much better return using this perfusion bioreactor design these days. So that's a more popular bioreactor design. And then there are these single-use bioreactors. What that means is you use single-use plastic bags as a bioreactor. See that right there? That's a bioreactor design. So since you don't have to do CIP and clean SIP, you just use this bag once and throw them away. So there's a much less time requirement for the CIP, SIP, and then validation processes. So it may be, cheaper just buying a bag and use it and throw away than hiring a lot of people and they'll do CIP, SIP. Okay, so single-use bioreactor technology is more popular these days. And process control is important. Like I said, all those probes and their monitoring, and then whatever the input you need to provide, that should be done automatically. So there's a computer software program will do that for you. Okay, take a look at it. All those dissolved oxygen level, CO2 level, pH level, temperature level, they'll be all controlled together. So so if needed, more oxygen will be pumped in through the gas sparger located right below the impeller, and then so the oxygen gas will be pumped in if it's needed. Okay, that's the reactor design. And if it's a pH control, the pH probe will measure the pH value, and if it's needed, you can pump in more alkaline solution to bring up the pH, because lactic acid will drop down the pH. Okay, so for your bioreactor setup, please visit this website. Just copy and paste the link, then you will see let me see this website I have opened up here for you. It explains operation of a bioreactor, benchtop bioreactor. Very good information. Read over that. And there's a video that you can play that will show you how you can work with the bioreactor in this short video. Okay, play that. I'm not going to play with you, so you do that in your own time. Okay, so that's it for this lecture 1. It's pretty lengthy. Okay.